The title, well, we were asked to reflect a little bit on our stay here, and I stayed here a month, and one thing you always have when you go to meetings with quite a lot of people that you don't know and who are from different disciplines, you get to learn lots of different acronyms. So there's here my adventures with all of these, and I guess most of you will know most of those. Process-based modeling, ecosystem services, uncertainty quantification, probabilistic risk analysis, machine learning, decision support, Bayesian belief networks, and beta biodiversity, and I could have added the whole Greek alphabet, obviously. It has been a big learning experience, and it has been very, very good. But at this moment in time, as we were talking at lunchtime, I think I'm more at the stage where I would like to sit and think for a month. And, so let's go through things. I will talk about landscape processes, because that's this section, and then landscape modeling and probabilistic methods, both focused on process-based models. So to stay in the theme, and a little bit of discussion at the end. Landscape processes. So now I asked myself, what is a landscape? And tried to look at a lot of literature, and then you come up with a definition. This is my definition. A landscape, LS, I use this in more slides, is an area with spatial connections and at least two types of managed ecosystem. Otherwise, it's just an ecosystem. You can have agricultural landscapes that many of us have been talking about, forest landscapes and such. So I showed some of this slide earlier, and then the question was raised, do we actually need a definition of landscape? And I'll make it multiple choice with just two possible answers. Yes, we must have a definition so we can focus. So we can focus our thinking, focus our research on the typical properties and problems at the landscape scale. And not every environmental and ecological model that we may happen to be familiar with is relevant for landscapes. But you can also argue the opposite. Landscape science is a young discipline. Thinking about landscapes is already happening for hundreds of years, but more as a scientific discipline, it's young. So don't stifle it with needless definitions. The premature definitions is also always bad in science. And most modeling and statistical methods are system agnostic. You can apply them to all kinds of systems. Well, when I came here, I was leaning for 90% to this one, to yes, and now it's 80%. So just a little bit more tolerance for not defining things. Landscape processes. Well, you think about spatial processes. Could we have to talk from James focusing on the biota? This is abiotic processes mainly. This is nitrogen flows in the landscape from crops that are being put somewhere, fed to cattle, and there's nitrate going through groundwater, and there's atmospheric fluxes. There are all kinds of connections, flows in the landscape that connect different elements to each other. And some of those we want, like fertilization, and many of those we don't want, and we call it then pollution. So, thinking about landscapes, well, that was already making us think about landscapes, all these processes that connect in a limited region. Well, make this long list of ecosystem services and ecosystem disservices. It's standard stuff, so I won't enumerate it. But I just want to make the point, and when you start thinking about any of these, you no longer start thinking like I tend to do as a biogeochemistry focused person on a field scale. No, we tend to start thinking about the landscape scale and how things move around. And I think all of these are important. So when we start thinking about landscapes, we have to think in a multivariate way. Data was mentioned, I think Lenks mentioned that it was not mentioned a lot in talks. I think that's true, but I think improvements are tremendous. There's fantastic data sets coming from remote sensing. The UK has this wonderful countryside survey where every 10 years square kilometers are intensively sampled. So there's some beautiful things coming up. There are many more data sets. So when we look at the landscape in the UK, then there's quite a lot of information. This kind of information from 8 or 9 different data sets to do with agriculture, forestry, and this countryside survey and the remote sensing can be combined to infer land use change over time, spatially distributed across the UK. And we wrote a paper on that. Peter Levy was the main driver there. So each of these boxes shows over time how land cover moved from one of these 6 categories to one of the 6 other ones. with an uncertainty quantification because we had the Bayesian approach. So getting nice data is becoming a reality. Other examples of that I learned about at this meeting, we had talks about the projects Assist and Eggland, and those are really interesting because they might lead to benchmark landscapes that are researched very, very well, and that can help people like myself who try to build process-based models, test our models and apply them. Other projects that have similar things are Advances and Advent. Not necessarily only agriculture landscapes, I think, but I should not talk about them. This is other people's work. We heard about very coarse resolution data sets. We had to talk about the FAO stat data, which of course are not at the landscape scale, but maybe occasionally coarse scale data can be used as a boundary condition or as prior information for prior probability distributions and such. Citizen science, well, I participate in the annual butterfly counting. As many people do, there's novel monitoring programs. We heard from Simon, I think, about people using smartphones to note things down. It is all quite wonderful. But still, indeed, the standard story is there's never enough. If you want to do specific modeling, then there's always issues with data availability. This is actually a study where people very, very closely looked at 6 different landscapes, all grassland-dominated agricultural landscapes in Europe, and did intensive measurements, made nitrogen budgets here. On the left-hand side are arrows of the nitrogen coming in from farming, deliberate, and from the top atmospheric deposition to the right harvesting products. But the important thing here for ecology is of course the surplus, the wastage, the nitrogen that leads to the groundwater and such. And you see huge differences between these different landscapes. And they are all of the same type, and they're all in Europe. And there is a huge variation that we have to take account of in our modeling. So how can we even start thinking about landscape modeling when within the small category of dairy farming or of landscape farming there are already such huge differences? How can we design models that are widely applicable? Well, I briefly mentioned that there's lots of research being done on the relationship between all kinds of complexity measures of landscapes and processes. I'll keep that very short. I learned at this workshop here that there are now quite nice collections of tools for quantifying certain aspects of landscape complexity, frac stats, landscape metrics, so those are good things. This problem has been raised a lot. Now we start thinking a bit more about processes, what is not so good. Data is getting better, but we still have eternal problems. Landscapes are complex and are varying length scales to all the transport processes. And processes, there's transport in the atmosphere, there's transport in groundwater, and the length scales vary enormously. Ammonia is typically not moving very far in a landscape, so if you have a chicken farm and there's lots of ammonia coming out, that is mainly doing its damage within the first kilometer. But if it's more oxygen-based nitrogen compounds, then they move much further. Well, pollen and seeds depends completely on the species you're talking about. Can be within 1 meter, can be tens of kilometers. I won't talk too much about the scale issues because we've been talking about that earlier. So this is a bit of an introduction about the processes that we all think about. And now landscape modeling. Personally, the next slide shows you my favorite book on modeling, and that is it's a novel by Hermann Hesse from 1943. I think many people know this book. May I ask, how many people know this book? Ah, good, excellent, quite a lot. I think it is magnificent. It is a novel. It describes a person who, in a future world, is learning the game, and the game is, you could say, it's a super form of Earth system modeling where everything is connected, where music, mathematics, everything we know is in there, as is described in this quote from the book. And the purpose is understanding, but the purpose is not decision support. So the theme of the book, so this is not what you as reader only think about, but the theme of the book is really the contradiction between possibly ivory tower complex modeling and how a person can be of use to society. I should stop talking about this book, it's just fantastic. Okay, back to modeling. So what can we do with these biogeochemistry models that try to integrate lots of different processes? This is a model for coffee that I made a number of years ago, and we feed it with landscape information on all kinds of variables to do with the soil and such. And we get output about the productivity of the coffee and the shade trees that are above the coffee layer in that landscape. And we can also get from the same biogeochemistry model other ecosystem surfaces being quantified: carbon sequestration, erosion, nitrogen leaching, nitrogen emission to the atmosphere. So that's nice, but obviously all of that is just the biogeochemistry bit of the landscape. So this is a very small selection of the ecosystem surfaces. They are all the flux-related ecosystem surfaces: productivity, carbon sequestration, nitrogen losses, and such. So this is what we do with our biogeochemistry models. And our drivers are the weather, the soil, and management from farmers and such. So if we then think about a topic like biodiversity, yeah, then in red are now on the slide all the things that we can't do with these models, that I can't do because I don't have this biodiversity modeling background. So there's herbivores, pests, diseases, pollinators, and they have all their own ecosystem surfaces that they bring, but they also affect the ecosystem surfaces that are flux. They regulate fluxes. So it's an interconnected system, so even when my model only looks at the biogeochemistry, it's not that I just forget about some ecosystem surfaces, but it's also likely that sometimes I simulate them less well than I should. So, well, this is partly because there's the scale difference. Biogeochemistry is often at the field scale and biodiversity modeling at the landscape scale. These things matter. So I often model on grasslands. So all this talk about we need to integrate is not just for the purpose of wanting to make our model more complicated. No, the literature is full of, I did not put the literature references here, but there are tons of them, full of mechanisms, responses that are known to depend on biodiversity, even though your primary interest might be productivity and such. So there's quite a fascinating literature, often with grasslands because they are so easy to manipulate, so there's also experimental literature. So it matters. I think when you don't look at this, then you have a too simplistic view of your landscape and such. We have been hearing about lots of types of different models. Now this is my scheme for a biogeochemistry model. This is Jenny's website and spatial network modeling with electrical circuit theory. There's lots of different models, so how can we make use optimally of the availability of all these different models? Just before I continue with that, just one example that colleagues of mine in Edinburgh work a lot on. This is about how air pollutants move in the landscape and how you can design a landscape to stop the movement of air pollutants. So this is not about moving of animals and that we've heard about, or plants, but this is how you can stop the movement of air pollutants, for example, from a farm. Here's a farm. By planting in the right places in your landscape shelter belts and such. Okay, so quite beautiful work is being done, but it's always just on small bits of the whole problem. But if we even just look at a simple question, which is not even covering everything, this biogeochemistry and biodiversity, how can we even link that up in a model? We are trying. I mean, in a group of people across Europe who are thinking about that and trying out little things. And we find that there are so many problems, and even to combine these two. So spatial scale, often the biodiversity models are looking at landscape or region, and we are with our biogeochemistry and productivity models just looking at a field. Model structure is very different. You have different state variables in the two types of models, so how to link them up. The processes are physiological, ecophysiological, or demographic in the two types of models often. Abiotic versus biotic. Data use is very different, and this is a technical hurdle, so the way the models are mathematically set up makes it difficult to combine them. There are some approaches. These are the ones we came up with actually only two that people have done to try to really combine biogeochemistry and biodiversity, and probabilistic approaches where you forget about your original implementation of the fluxes and the mechanisms and such, but move to a Bayesian belief network, for example, which is a different representation. And this is an interesting approach where you simplify the dynamics of your multi-species grassland sward, for example, by having effective parameterization. So the parameterization that corresponds to the abundances of the components of your sward. And this works, this last method, I never believed it could work because it does not explicitly simulate competition. But it seems to work very well. Here are 4 time series for, the measurements are the symbols for 4 different grassland species who are together in one sward, and depending on the time of year and environmental conditions, one goes up and the other goes down, and so on. And this can be modeled quite well. I think it is possible because this is still a quite simple system. Far more ambitious is model coupling, where we, now this slide we have seen a lot from Paula and Amy and others work on this, where we of course have the questions how to test such integrated model frameworks, not test the components, but test the framework, how to manage the computing demand, how to do the uncertainty quantification. So those are obvious questions then. So having led to those obvious questions for that kind of complicated situation, I now want to say a little bit about probabilistic methods, because that has been a huge focus of this meeting, and it has been very inspiring. There are lots of people present who know lots about this, so everybody can learn. I learned a lot. And I will start from something that I wrote 2 years ago. This was in a quite obscure journal. I looked at Bayesian methods for uncertainty quantification and forest process-based models. But if you talk about methods like that, it can be actually any kind of ecosystem or landscape. And I came up with a list of 11 trends that I thought were happening in this area of applied science. And I don't want to go through all of them one by one, but instead there's 2 things. First, which of these have been discussed? Well, I found that 8 were discussed in the past month. I cannot say that these 3 have not been discussed because people have been talking all the time everywhere in different rooms. So probably everything has been talked about. I just group-wise want to talk about these 3 groups of issues. This is ensemble modeling. We have not talked about that. I think I had a question mark there, where you have multiple models for the same thing. So not different models for different aspects of the system, but multiple models for the same thing. And I think that is tremendously valuable to have those all combined. You learn from the differences. There is this famous paper by Chamberlain from 1890 in Science, the method of multiple working hypothesis, where he effectively says that this is what you should do. Because otherwise you keep hanging in your favorite theory. Parental affection for a favorite theory. Instead, you should have multiple models, I translate this, that you weigh the evidence of. So he was, this is actually quite a nice paper to read. It is very, just 6 pages, it's online. So we've done this kind of thing with forest modeling. There are 6 forest models mentioned here. And the Bayesian model averaging is then, after you've calibrated the models, have assigned posterior probabilities to the individual models, and have then the probability weighted averaging going on. You can compare with observations how the 6 different models and the Bayesian model averaging in blue did before calibration and after calibration. And there's 2 kinds of calibration here, country by country. This was done in different countries of Europe. Or generic, where you have the hope that one kind of parameterization of your model is okay everywhere. My model, unfortunately, did not have a high posterior probability. That's BAS4. So I was a little bit disappointed, but I was leading this exercise, so it's always good that your own model doesn't come out the best. So that was okay. What I find very beautiful, this is a paper by Richard Chandler, is this way of thinking about things when you have multiple models. So he wrote this paper where it's just a diagram essentially, looking at how to combine different climate models. There was his paper. If reality is here, if the behavior of the real world is here, then we might have a cluster of models which have different kinds of behavior, so the models differ from each other. You might assign a center point to the midst of the cluster. So you can split up the differences between models and reality by looking at the big step here from reality to the center of the cluster and the individual differences of the models to that. I think this is a very realistic picture, because we know from climate model history that at some point they all realized that aerosols had to be introduced. So they all shifted to a different location in behavioral space. So there are joint biases in models, and not just in climate models, but I think with most disciplines there will be joint biases. We may not be aware of them. So I think this is a good way of thinking about things, and he works in this paper towards the thinking about how to implement this and do something with it, but actually stops quite short, so there's still a lot of thinking by clever people to be done. I talked with Michael Goldstein about this, and he said that you can indeed, if you look at this paper by Richard Chandler, identify this step here with his external discrepancy, and these differences here with your internal, not identify, but relate the internal discrepancy to that one. Where discrepancy is Michael's term, for those who were not there, for the difference between truth and what a model says. So this is structural error of a model. So that was, I think this is a good way of thinking. Then I take these together, trends in use of novel ways to account for model structural error in calibration, general software for Bayesian calibration of complex models, fast MCMC algorithms. I don't think anybody spoke about that. And more use and novel types of model emulators. A lot was talked about this, and I thought it was fantastic. So we had people here who knew a lot about this stuff and came up with their ideas, criticized existing methods, and came up with concrete alternatives that we could look at. So managing uncertainty in complex models is a huge topic, and it was a huge topic here this past month. And it is not just about one thing. Everything, you should see everything together. So it's not just one technique here, one technique there. It's a way of thinking that applies to everything. So emulation, pre-calibration, calibration, prediction, all of them have to do with uncertainties in one framework. We got explanation, Victoria gave us a demonstration of the extra UQ software, Danny involved obviously. I just want to point out that from my own experience there are other kinds of software which perhaps are less good. I cannot evaluate that, but that we in our forest and grassland modeling disciplines do use. Pecan in America from Mike Dietz, Bayesian tools from Florian Hartig, and yesterday I heard from Mark that Nimble is quite good software. Emulation is becoming increasingly powerful. We had a fantastic demonstration with Oli Worley of Bayesian hierarchical emulation for multivariate spatiotemporal input and output. Well, if you read this, he's tackling quite a lot of stuff here. This is no longer emulation of a scalar, one single output of a model. No, this is looking at variation in space and time, and from multivariate to multiple different variables considered as well in a hierarchical approach. I sat down with him for an hour or two and he explained things to me. I think it's wonderful where this is going. But there are alternatives to this essentially Gaussian process-based stochastic emulation. There are methods in the literature for model simplification that we did not discuss, but I just wanted to point out two that I happen to know of. The approach by Peter Young, where he takes methods from control theory, systems identification methods to come up with simplifications of differential equation models such that the result is still a differential equation model but of lower dimension. So there's still mechanism there. And the same idea of simplifying a model by the group of Neil Kraut with a semi-Bayesian way of replacing variables with constants also aims to still preserve the mechanism, not replace your model with statistical emulator, but have mechanism in there. And I think maybe we can spend a bit more time as a community making these methods richer than they are at the moment. The one criticism of the top one is that it is not powerful enough to look at multivariate results. Okay, the general thinking behind these simplification approaches, I think it is comparable in philosophy to what Roddy talks about. It is try to not have unneeded, unnecessary mechanisms in your model. I think that can be helpful. Next group, this was at the bottom of my list. Visualization techniques, more use of graphical modeling. I don't think we talked much about that. Risk analysis. We had Freeman and Spiegelhalter, this fantastic lunch where they talked about their Center for Risk Communication, and we had this nice interaction with question and answers on communication of uncertainty. Just one pointer to a paper by colleagues of mine who combined GIS methods and Bayesian belief networks for landscape design in interaction with stakeholders to find out where in a certain region in the Alps, French Alps, you would put your productivity forest and where you put your conservation forest. So I think this is in the area of visualization, communication, and such. Then risk analysis. I talked about that, not with great success. This was risk defined as an expected loss. It's a probability of a hazard times vulnerability. I thought it was nice that you can quantify this risk for example, drought risk in Europe as the product of the drought probability and vulnerability. The discussions were very, very good. I learned a lot from that, and I do still see value in this approach for communicating this to other people, and I notice this very frequently. You can talk about these things in these simple terms as risks and its components, and that is valuable, and I think we should continue on that path, but also consider, and that was the suggestion I got, to use a more general approach that facilitates uncertainty quantification and decision support. So effectively use Bayesian decision theory to evaluate action portfolios. So go directly to uncertainties and actions rather than this specific quantification of the risks. I think we should do both. I think I'm nearly there. Oh yeah, just some extra topics that were not on my list of 2 years ago. Bayesian meta-analysis we heard about from Rebecca and Gavin. Model diagnostics and design and machine learning. Those are the only things I'm going to add. This is about diagnosis and design. So I hope that we did not talk much about that. This is diagnosing how models can be bad and where the weaknesses are. Maybe there are more things that we can do, statistical methods that can help us and such. We're already using the methods for this adaptive sampling, so where you put a sensor in a landscape and how to move it around. There's literature on that. And for designing landscapes, Jenny talked about that. But here, models, not so much. We did not talk so much. There is, just to give a flavor, very nice decomposition by Kobayashi and Salam from the year 2000. If you have two time series, measured and a modeled one, you can calculate the mean squared deviation, the mean squared difference between the two, and decompose that in different terms, each of which you can interpret, and they point to certain problems with your model. So this is a very simple technique to get in the direction of where a model could be improved. So my question is, can we do more like this kind of thing? The lure of machine learning. I know this is what I thought, mentioned in bullet points of many talks, but rarely discussed in detail, and I'm going to do the same thing. The feeling I now have, not knowing much about it, is that it indeed has strong roots in statistics, that are techniques that lead up towards modern machine learning. But it's of course computationally and algorithmically very much evolved. The eternal question of what then happens in your black box will never go away. There's this very well-known book by Cathy O'Neill from 2016, Weapons of Math Destruction, where she points to the dangers of letting algorithms decide in society, for example, whether you can afford to get a loan or so. Then the more positive way forward could perhaps be, how can we combine these machine learning techniques with automated pattern recognition, with mechanistic understanding. And you all will have seen this paper by Marcus Reichstein a few months ago, Deep Learning and Process Understanding for Data-Driven Earth System Science. The way they describe the possible ways machine learning or deep learning and mechanistic modeling can work together, I think applies to every field. But they focused on Earth system science. Last slide. Discussion, it's more summary, so it can be very quick. Are we taking the landscape scale seriously enough? So with 80% certainty I would say no. Landscapes are difficult to model. We may want to keep models separate rather than couple them, is a statement I would like to make. And there are many uncertainties, so probabilistic thinking is essential. And the bits here are just probably a repetition of what I said. Thank you.